Hello everyone, this is Amrain and today we are going to discuss a numerical related to compression member, that is built up column. I am going to design today a column with a single lashing system. Okay, so I'll show you a diagram. It is available here. See, single lashing system. We have two channels with certain spacing. So let's go through question. Design a built-up column 10 meter long to carry a factor axile load of 1080 kN. The column is restrained in position but not in a direction at both of the ends. See, this line is really so much important. So please go through it once again. The column is restrained in a position but not in the direction at both of the ends. So the question is saying like it is restrained by translation. So see, you can see here you will get some value for okay, so your question was restrained in position but not in the direction. Okay, so according to conditions the value will vary. So the translation is completely restrained at both of the ends while rotation is free at both of the ends, right? Because not in the direction. So our condition is the translation is restrained by position, right, at both of the ends, and the rotation is free, that is at both of the ends. So the value is 1 times length. So your effective length is 1 times L. So similarly you can go for different value according to different conditions. So the conditions they will give you in question. So according to that different conditions you can take different value. Fine. So you can get this from table 11 of your code book, IS 800 2007. So now provide a lashing system with the bolted connection. Assume steel of a grade Fe410 and a bolt of grade 4.6. So the grade of steel is given you 410 and the grade of bolt is 4.6, and it is asked to design the column with the two channels placed back to back. So sometimes they might ask you toe to toe. Actually I am going to design the column with two channels placed back to back. In my next video I will explain you toe to toe. Okay, so for a moment I'll show you what's the difference between back to back and toe to toe. See, back to back means like flanges of channel are facing opposite to each other. Okay, they are not facing to each other. In a toe to toe you can see that flanges of channel are facing towards each other, they are facing to each other. Okay, but in this case they are not facing to each other. Okay, so this is known as a back to back and this is known as a toe to toe. So according to the conditions the formula varies here, that to find value of S, okay, to find the value of S it will vary. I'll explain you that in a numerical. Fine. So this is the difference between the distance between one edge of the channel to other edge is S. In this also here also the same condition, the distance between one of the channel to other edge of channel is also denoted by S only. Okay, that is spacing. So you will be more clear in numerical. Fine. So solution, the grade of steel is given Fe410, so Fe will be 410 megapascal, yield stress Fe will be 250 megapascal. Similarly grade of bolt is given, that is 4.6, so obviously Fe will be 400 megapascal because 4 times 100 400. Suppose the grade of bolt is 8.8, then it will be 8 times 100 800. Okay, similarly it will go in that way. Partial safety factor for material, gamma m not 1.10, gamma m be 1.25, gamma m double 1.50. All these value you will get from code book. Fine. So now we have to design the column. So load is given 1080 kilonewton, 1080 kilonewton times 10 to the power 3. I am converting into Newton, and length is obviously we know that 1 times length L, so 1 times L will be 10 meter. The exact compressive stress I took here is 150 megapascal. Actually you are allowed to take between 125 to 175 megapascal. Okay, so from this value 125 to 175 you are allowed to take any value. Actually I took 150 to, so you can better adapt to 150, it won't make you any problem. Cross section area required is equal to P by allowable axial compressive stress. So what is P? 1080 into 10 power 3 Similarly 150 megapascal is our axial compressive stress. So total area I got is 7200. So this 7200 mm square is a total area for two channels, not for one channels. Okay, it is for two channels. So if you go for one channels, it will be 3600. So I have to select ISMC, that is I have to select a channel in a such a way, I have to select such type of channel in a such a way whose area is more than a 3600 mm square. Fine. So I went for 300, ISMC 300. See, the area is 4564. It is more than 3600 square. Actually, you can add up 250, but I did that. I add up. Initially, I took a 250 whose area is more than 3600. You can see here. ISMC 250 whose area is more than 3600, right? 3867 mm square. Actually it is in centimeter square, cm square. See here, it is in cm square. I took mm square. So 3867 square. But it is not satisfying the conditions. See, we have to get a value, we have to get a design compressive strength PD more than 1080 kilonewton. So when I took ISMC 250, then I got a value which is less than 1080 kilonewton. So obviously if I get less than 1080 kilonewton, it won't be a value of more than 1080 kilonewton, right? That's why I took again ISMC 300 at the rate 351.2 newton per meter, 2 in numbers. So you can try once 250 and you can check the value. Okay, similarly way you can check the value what you will get. Okay, so but you will get more value in ISMC only 300. So don't go for more than this, okay, because this is satisfying our conditions. So the relevant properties of ISMC at the rate 351.2 newton meter per meter are all this property you can get from codebook. So please go to the table. I am showing here details, so please look at this table. I am showing here the tables and your codebook pages, so not pages but codebook where it is available, so it will be more easy for you guys. See, ISMC 300, all the value you can get from here. See, you will get every value from this line, okay, and the notation is at the top. Fine. So from this notation, with help of this notation, you can get all required value, all important value. Okay, so let's go to our question. So you can get all this value. Now total area, because you have two number of channels, right? So 2 into 4 5 6 4, that is 9128 mm square. Fine. So minimum radius of gyration RZ is equal to 118.1 mm. Actually, see, there is one conditions for us. Okay, before designing the channels, there is one very important condition, and that condition is that the sections are so spaced that radius of gyration of the section about the axis perpendicular to the plane of lashing is not less than radius of gyration about the axis in a plane of lashing. Okay, so this is achieved by making radius of gyration about YY axis equal to or greater than radius of gyration ZZ axis. And we know that from slenderness ratio L by least radius of gyration. So in this case, if I took RZ here, then obviously RY will be either equal to or greater than RZ. That's why always try to take RZ here. Okay, so 10 into 10 power cube by 118.1 84.6740 will get this value. So please don't be more confused, because I am saying here minimum radius of gyration. If you compare here RY and RZ, you are getting RZ is more. Actually condition is saying like that RY must be greater or equal to than our RZ. So to fulfill that conditions, we have to take least, that is the least value, RZ. So automatically RY will be either equal to or greater than RZ by the conditions. Okay, by the theoretical conditions. So for that conditions I took this value. So you also please better to take RZ. Okay, so effective slenderness ratio KL by RE. So 1.05. See, actually I have increased here 5%. The normal value is 1, right? 1 into 84.674, but it is here 1.05. So I increase here by 5%. Why I did it is so because the shear deformation is occurred in this case, in column case. So to account a shear deformation, I have to increase by 5%. Okay, so I'll show you here diagram so you'll be more clear. See here, see this column, so there is chances of a shear deformation. So to account that conditions, we have to increase by 5%. Okay, so try to increase 5%, whatever the you will get value of k. So try to increase 5% and KL by R naught. Okay, fine. So always try to increase 5%. See, our effective slenderness ratio is 88.90, Fy 250 megapascal, and buckling curve C. So how you know this is buckling curve C? So you can know this from table. Okay, so we know the buckling curve C from cross section, right? So see our cross section, these are cross section, right? Please go to table 10, buckling class of cross section. Okay, clause 7.1.2.2. under this there is a one table 10. So there is a buckling class C, buckling class, and you have to see the cross section, which cross section it belongs to this. Okay, so C, buckling class is C. Okay, so according to, if you have a I section, then it may be A, B, or B, C. Again you have to see this certain conditions. So according to these conditions you have to choose which class it is. Okay, but in our case it is a simple like C channel type C, so you can take C. So we got KL by RE, we got Fi, we know the buckling class, it is C, buckling curve C or class C. So FCD is 122.65 Newton per mm square. You got this value by interpolating. See, interpolation is required here. You have to go to table, you have to go to the code book. In code book there is one table for us, design compressive stress FCD for column buckling class C. Okay, so see KL by R, you got this value, right? 88 and 90. Between 88 and 90 our value is 88.90. there is one value, so 80, 88.90 and 90. Similarly, see here under 250, 136 and 121. So you must get value between these two. So 136, suppose value X, and 121. So we have to find X, right? So we can get this value X by interpolation. So I did same thing and I got the value FCD is equal to 122.65. So that's why I am showing you code book pages, so it will be more easy for you guys to find out where the value is available. So the design compressive strength PD is equal to FCD times AE. So FCD we know 122.65 into total area. You know this is the total area because I have already told it is for two channels, right? So obviously 2 times 4564 9128 mm square. Okay, so this is the value. We got more than 1080 kilonewton. So obviously if I get more than 1080 kilonewton, then obviously it will bear the load up to 1080 kilonewton, right? So no doubt for that. So now for next part, our first part is completed. For next part we have already defined the channels. So the spacing of channels is really so much important. So to find the spacing of channels, let us provide the two channels back to back, it is right, and then connect with a lashing plate. So spacing of channel, what is our condition? Ry must be greater or equal to Rz. So obviously we get this relation. You know that Iy by A, Rz is under the root Iz by A. So here see, in this case don't be confused, Iz and Ix or Rx and Rz, it is same thing. Okay, so don't be confused. Fine. So you know this formula for unsymmetric section. You know this formula I for unsymmetric section. You have already read in, I think, strength of material and other subject. So ICG plus A times Z bar square or X bar square, ICG plus A times Y bar square. So in this case, see IY plus A spacing by 2 plus CYY square. In this case we don't have CXX, so it is 0. So normally if I'll say okay, this value ix times 2 I wrote this side. Okay, see here, this value I wrote at this side. Okay, and this value I wrote at this side. Don't be confused. See, it is like crossing to each other. So this value I wrote at this side and this value I wrote at this side. So 2 times iz, 2 times this value, all value, and all value is available in code book. Okay, so now see, one there is confusion, that is s by 2 by plus cyy. Okay, so see, one scene diagram, don't be confused. Scene diagram, here you go. See, this is cyy, right? This is cyy, right? This, up to this distance it is cyy, and we have to take a center distance from both of the channels. So for both of the channels, this is cyy, we have another channel this side, right? There is cyy, and middle is s by 2. So here we have a clear diagram for that. You can see here, see, suppose this is cyy and we have a middle point s by 2. So the centroidal distance, right? So the centroidal distance between two channel we have to find. Fine. So for that conditions I did s by 2 plus cyy. Okay, total area times the centroidal distance, right? So area times s by 2 plus cyy will be centroidal distance for two channels. So spacing I'll get s is equal to this much, 183.10 mm. Okay, by solving this, because all this value it is written at the top. See, you will get all the value from here. Fine. And if you are getting more confused, then directly it is like a formula type. So you can just remember this is the formula type. Try to don't mug up. Try to understand how it came. So it is like formula type. If you feel little tough, so don't forget. So directly you can replace the value and you can get the value of s. Okay. So better try to understand the conditions before mug upping. Try to know how it came, and then you can, it will be more easy for you guys. Okay, so you can directly connect, get idea from this figure and then next figure. So this is s by 2. So actually I have not shown here clear diagram. Now we know the spacing s is 183.5 mm. Okay, so lashing system, let us try a single lashing system. Assume the inclination bar 45 degree. See, I took here the angle, this theta, okay, this is our theta, this inclination, right, to longitudinal axis, this inclination to longitudinal axis. So you are allowed to take between 40 degree to 70 degree. Okay, you are allowed to take between 40 degree to 70 degree. So I took here 45 degree. Better add up 45 degree, it will be more easy for you guys. Okay, so now you see here A1. Before saying this, okay, let's say this, then I'll say you another. Let me explain this. 2 times 183.5. So spacing is 183.5. We got right from above expression. And 50, the 50 distance g, it is available in given data. See, g, g 50 mm. Okay, g 50 plus 50. So your centroidal distance between two channel is, this is the total centroidal distance between two channel. Okay, this is the total centroidal distance between two channel. Fine. Now what I did, cot theta, so I multiplied by 2. Okay, so I'm explaining you here. See, you got the value 183 plus 50, 50. So total you got the value 283.5, right? So suppose this is horizontal value 283.5. To get a vertical value, so that horizontal value is b, right? So suppose this is b, and to get vertical value a, we know that tan theta is equal to b by a, right? So a is b by tan theta, b is cot theta, a is equal to b cot theta. So distance a is b cot theta. So horizontal distance times cot theta, right? Yes, vertical distance is horizontal distance times cot theta, and I need the value A1, that is the lashing flat of from this end to the lashing flat of another end. See, up to this end. So total I need this value. So A for this channel, for this lashing we have one value A, for another lashing we have value A. So we need total A1, that is 2 times of A, right? 2 times of A. So it is very clear, A1 is equal to 2 times of A. So in our case, see, 183.5 plus 50 is horizontal distance, into cot theta I got a vertical distance A, into 2 I got total distance. Yes, so 2 times A is A1. So same thing it is happening here. See, 183 plus 50 plus 50 plus 183 plus 50 times cot theta, I'll get this value, times 2 I'll get up to this end. Clear? So 567 mm. Fine. So there is one conditions, A1 by Ry must be less than 50 or must be less than 0.7 times 88.90. 88.90 I think it is KL by R, right? It is at the top. See here, KL by R, 88.90. Okay. So you will get that value. Now we got all this, all conditions are satisfied up to here. So now maximum shear, transverse shear in each panel, and compressive force in each lashing bar. Before explaining this, I am going to show you a diagram that is more easy. See, the force acting Bt by N in this direction, obviously it is compressive force, right? So compressive force, you know the geometry property, right? If it is theta, then obviously this will be Bt by N cosec theta, right? So this is the Bt by N cosec theta. See here, it is showing here theta. Now vertical load at the bolt. So at the bolt, the vertical load, it will be acting at Bt by N cot theta. So these all from geometry, you know very well. Just it is a Pythagoras theorem. So you apply that and you can get all the, not the tan theta and like sin theta some people have. Perpendicular by hypotenuse. So in this way you can get all the value and you can go for calculation. So in simple manner, just understand Bt by N will be act like transverse, Bt by N cot theta it is a vertical, and Bt by N cosec theta is inclination. Okay, simple, it is very simple. So I'll explain you. See here. Now let's go in our question. Maximum shear is Bt, it is 2.5% of total load. Okay, always maximum shear force is the 2.5% of total load. So 2.5% means 2.5 by 100 into total load. We will get 27,000 Newton. Okay, this is the maximum shear force. Now, what is the transverse shear in each channel? Transverse shear, we know that transverse shear, right? What is the transverse shear in each channel? Transverse shear Bt by N, right? So transverse shears Bt by N. So 27,000 by 2. Okay, I write here 27,000 by 2. So N is equal to 2 for 2 channels lashed on both faces. Okay, that's why it is a 2. I'm again saying you the N is equal to 2 for 2 channels lashed on both the faces, right? That's why it is a 2. Now see, compressive force in lashing bar. So compressive force is like Bt by N cosec theta. Obviously you will go for if you make a theta this, and this is your Bt by N. If you are going to find this, then it will be like this distance. Suppose this is the Bt by N distance, for example, assume it, and this is the h, you have to find hypotenuse, right? So if you are going to find this, then obviously it will be Bt by N sin theta. So if I'll convert in, if 1 by sin theta is equal to cosec theta, same thing, right? So you will get this compressive force Bt by N cosec theta. It's all about geometry, nothing more complex. See, you can know more from here. See, if it is a theta, then what is our sin theta? B by this distance, right? B by this distance. Okay, so to find this distance, obviously B by sin theta. So you will get that B cosec theta. So similarly way you got here Vt by n cosec theta. So obviously try to understand a simple way. This force is always Vt by n cosec theta. That is compressive force between one inner bolt of one to other bolt. See. So now obviously it is Vt by n cosec theta. So you'll get this value. Fine. Now we are going to assume a diameter of bolt. We are assuming a 16 mm dia of a bolt of grade 4.6. So obviously now we have to find the minimum thickness of lacing flat. So thickness means see here I will show you diagram. Diagram is this. Okay, thickness, it has got a certain thickness. It is a width and it will have a thickness. So the thickness of lacing flat, we have got one codal provision, codal formula. Let's say minimum thickness of lacing flat 1 by 40 length of the flat between inner in bolt. Okay, so the length between this, from this bolt to this bolt, length between this bolt to this bolt, and obviously you know to calculate that because you know the horizontal distance. If you know the horizontal distance, 183.5 plus 50 plus 50 cosec 45 degree is your this distance from this bolt to this bolt. Okay, so you know the horizontal distance. So horizontal distance times cosec 45 degree, you will get this distance, right? All these things is about geometry. Just try to understand geometry. That's it. Now to calculate minimum thickness, minimum width of the lacing flat, sorry, as specified by IS code, it is 3 times either this of diameter, that is 48 mm, or it must be not less than 50 mm. Okay, so either 16 dia into 3 times of diameter or not less than 50. So I took a 50 mm. I took width of the flat is 50 mm. So the width of the flat is 50 mm, and the thickness of the flat is 1 by 40 length of the flat between inner in bolt. So 1 by 40 inner in bolt. You know that this formula because I already explained you the 50, 183 and 50. Just find out this as hypotenuse distance. Okay, you know the theta, so you can get that distance. So I got 10.02 mm, which is approximately equal to 12 mm. Fine. Now there is one condition: minimum radius of gyration are t by 1 by 12. So that is 12 by 102. Actually this distance you can get very easily. It is I wrote here directly, so you can write here t by 112. No problem for that. Okay, so you know the value of thickness 12 I took, so just 12 under 12. Actually in class I think I have told about this. L by R. So we know that total length, and we know the R what we got here. See, okay, so we got the value which must be less than 125, so which is all right. Now buckling class L by R 115.72, Fy 250 megapascal, and buckling class curve C. Okay, so again same thing, we know the value L by R, Fy, and buckling class C. We can go to the code page number, not page number, let's say table like this, table 9.c, and you can interpolate this value and you can get a value FCD. See, you can get the value FCD. So we know that thickness of the flat, width of the flat into FCD, the load you get 53.02 kN, which is greater than 9.09 kN. It is all right, which is sufficient. Now we have to find out the tensile strength of a plate, that is a flat plate, that is a lacing bar. Okay, flat. So you know that 0.9 into net area by Fu by gamma m1. So what is our net area? Total width minus diameter of dia of whole plate. There is a whole 16 plus 2. Okay, 18 into thickness is 12. So you can get the net area. You know to better to find this. Gross area you can find this because you know the 50 and 12 width and thickness. So gross area you can get. So now connection we have to go for connection. So for connection, dia bolt we know that 16 mm grade 4.6, so obviously FEB will be 400, and strength of bolt in double shear it is like double shear. See, 2 times A and B, NN value is here 2. How it is 2? See in diagram. This is double shear. One lacing bar is connected to other lacing bar. So the interface is 1. Again this lacing bar is connected to this channel. So the another interface you will get here. Okay. So you are I hope you are understanding. One lacing bar is connected to other lacing bar. So the interface is 1. And again this lacing bar is connected to other channel. So if you see this, there is a two layer. This channel and a upper lacing bar will make one layer. Connection is there, it is attaching at one point, and this lacing bar and this lacing bar will make one layer. So obviously interface is 2, so that's why I took here nn is equal to 2, nn is equal to 2. Wait, it is below, I think. Nn is equal to, you know, the A and B, 0.78 times the area, and then FUV, you know the value, root 3, you know the value, gamma MB, you know the value. So just place the value. Similarly, you can go for bearing. You know all this value because I have already explained this in first, second classes. So you know all those value. So you can get directly, and then you have to find out the minimum value, which is minimum. So obviously 58.01 kilonewton is minimum value. So you better choose minimum value. So minimum value is 58.01 kilonewton. Now force on a bolt from lacing plate. What is the force on bolt from lacing plate? So force on bolt, I have already told you, 2 times Bt by n cot theta. See here the lacing plate how it makes force. See from this 2 Bt by n cot theta. The Bt by n cot theta is your vertical load, right? See, you know the value. See, this is the theta, this is the theta, you know this Bt by n. So if you convert in vertical load, obviously Bt by n cot theta, it is all geometry. Okay, so due to the two lacing bars, you are getting here 2 times Bt by n cot theta. So total force 27.0 kilonewton. So number of bolt required, I have already told you, number of bolt required. Total force by strength of a bolt, either in shearing or bearing, which is minimum. So 58 is minimum, so 0.456, so which is equal to 1. So better give 1 bolt. Okay, so that's why you can see in diagram. See here, I have provided just a 1 bolt. See, 1 bolt here and 1 bolt here. Okay, just 1 bolt. Okay, so I give a 1 bolt. See, 1 bolt. Now tie plates. This is your tie plate. See here in figure. See, this is the tie plate connecting the end plate, which is connecting both of the channels. See, this is the tie plate. Okay, so in this case, you better can find the horizontal distance, right? Width of the channel. So you know that 183.5 plus this distance is your horizontal distance, right? So this is the horizontal distance. See, 183 point effective depth, there is a formula, spacing plus 2 times of cy. So this must be not less than 2 times 90 mm, which is alright. Overall depth of the plate is 230.7 plus 2 times 30. Okay, so overall depth of the plate is 230.7 plus 2 times of 30, that is minimum edge distance. So the minimum edge distance is 16 mm bolt. Okay, so for minimum edge distance for 60 mm bolt, 1.5 times the hole, that is 16 plus 2, it is 18, right? So 16 plus 2 is your 18. 18 times 1.5 will get 27. So approximately I took 30. So you have to overall depth of the plate is 2 times of minimum edge distance. So for one side I got a 30, for another side it is 30. So 2 times I did 30 plus 230.7. Okay, so 230.7 plus 2 times 30 will give 290.7, that is around approx 300 I took. That is the overall depth. And obviously for horizontal it is very easy. You know the this value, like spacing 183 and the width of the flange is 90, right? Width of the flange is 90. So total this distance you can calculate easily, 183 plus 90 and this 90. So total distance you will get 90. So 360.5, 364. So for thickness of plate, tie plate, you can do 150 by total distance. 153.50 plus 2 times 50, that is G. I have already told you. So you will get around 6 mm. So I have provided here type plate of 364 times 300 times 6 mm. So it is very much easy. You don't have to worry. Effective depth is S plus 2 times CYY. Overall depth of plate is whatever the distance you got here plus 2 times minimum edge distance, and you know the minimum edge distance to calculate. And length of the type plate, you know that spacing plus flanges, total flanges, and thickness of type plate is 1 by 50 S plus 2 times G, that is 50, right? So you can get 6 mm. So total we got value 364, 360. I have shown you in this figure. See, 300 total 364, and thickness, the plate thickness is 6 mm. That's all, friend. So in next video I'll explain you about tau to tau. Okay, thank you so much.